Hi, so let's take a look at part 2 of related rates. So our next example that we are going to look at is the ladder problem. You'll see this one always shows up in the AP, these right triangle problems. So it always kind of starts off with something like we are given a ladder. In this case, we have a ladder that's 25 feet leaning against the wall. So I know that this ladder is 25 feet, so I'm just going to say that. The foot of the ladder, that's down here. Remember, this is the ladder. So the foot of the ladder is being pulled away from the bottom of the wall at a rate of 14 feet per second. Notice they're giving us that rate, so we know that this is a derivative. It is a rate of change. So it's being pulled in this direction, right there, along the ground. At what rate is the top of the ladder, so there's the top of our ladder, moving down the wall when the ladder is 7 feet from the ground? That's a big major typo there. So before we begin, the one thing I want to tell you is the secret to related rates. This is the big secret. And this is it. If it changes, it gets a variable. So I'm going to have to define all my variables when I do my givens. So I'm going to look at the picture now and look at anything that changes. Oops, sorry. So if I look at the ladder, is the ladder going to change length as it falls down the wall? Of course not. This is constant. Constants just stay the same. But will the length of the top of the ladder and the wall change? Of course. As the ladder goes down the wall, this distance will change. This length will change. This length changes. So we're going to just call that W. It's going to be a variable. Next, what about the bottom of the ladder and the ground? Of course this is going to change. So we're going to just call that G. Right, so now that we have everything, now we're going to go ahead and write out our givens. The first thing we're told is that the ladder is being pulled away from the bottom of the wall at 14 feet per second. So let's talk about the change in the ground distance. So that's going to be the change in the ground distance over the change in time. And it's getting, the distance is getting further, so it's going to become 14 feet per second. Now, another thing I want to tell you is this is another hint. How I know it's positive. If the distance from an object increases, we say the rate is positive. If the distance from an object decreases, we say the rate is negative, less than 0. So because the ladder is moving away from the wall, we know that this distance is going to be this rate is going to be a positive 14 feet per second. Now, then we're told that the top of the ladder is 7 feet from the ground. So that's telling me that W is 7. And then they tell us we want to find out the rate at which the top of the ladder is moving. So we're trying to find the change in the wall length. So dW dt. That is what we are trying to find. Right there. So let's come up with a geometry equation. Remember, we're going to look at a formula. And in this case, it's not so bad. We have a right triangle. So I can say that G squared, remember, the ground length of the ladder is changing. So I'm going to leave that as G squared. The height of the wall is changing. W squared equals 25 squared. And remember, this is a constant, which is why I leave it as 25 and I don't give it like some sort of variable. It makes it more fun if the ladder is changing height too. And we will see a problem like that coming up soon. At this point now, I can start taking the derivative because remember, these are my values. I want to find the rates of change. So I take the derivative. The first one's pretty easy. 2g, don't forget it is implicit, dg dt plus 2w dw dt. And this is why we love constants. Their derivative is 0. All right, so let's take a look here. If you're good, you can just divide out everything by the 2, and you're okay with that. You don't have to divide everything by 2, but it doesn't hurt to do that. Now, we are given W, we are given dg, we are given W, we are given dg, and we're looking for dw. What we don't have is g, so that's what we have to find first. We need g here, so we have to find g in our equation. To do that, I can use my formula. G squared plus 7 squared equals 25 squared. And if you solve this, you get 24 for G. And I can just plug in 24 dg dt equals W. Plus. I messed up there. Give me a second here. Erase. I'll just start over there. There we go. We're given 24. dg dt, we're told, is 14. Plus W, which is 7. dw dt, which is 0. So in solving it, we get W dw dt, and you're going to wind up with a negative 24 times 14 over 7, or negative 48. So let's talk units. Again, here's our big, not red, I like green. When we look at the units here, the width, W, the height of the wall, is in feet. And T, maybe that's a T, it's a weird looking T there, is in seconds. Now, if you notice, this is negative. This is less than 0. Therefore, this is telling me that the height is decreasing. That's what we said up here. If the rate is less than 0, that means our distance is decreasing. So when we write our answer, we can say the top of the ladder, when W is 7 feet, is decreasing at a rate of 48 feet per second. Now be careful. Notice we're saying this is decreasing, but we keep that positive. Even though it's negative, the negative tells me it's decreasing. The 48 is just a number for it. It's a scalar, like in physics. Okay? The decreasing is also negative. Never say decreasing at a negative. So don't say decreasing at negative 48, because that's like a double negative. That means it's actually increasing. So we don't write that. Good. I hope you had fun with this one. This is like one of my favorite questions. This and the next one right here, the cone problem. Okay, you're going to see this one on the AP. This one always shows up sometime. This one always shows up like 99% of the time. So water is running out of a conical tank at a rate of 2 cubic feet per minute. So like one of the other examples we did in the other video, this is my volume. This is my change in volume. The radius at the top of the tank is 5 feet. And the height of the tank is 10 feet. Now notice, this is dealing with the tank. How fast is the water level changing? So we're looking for that change in volume, dV dt, when the water has 4 feet, when the height of the water is 4 feet. So one thing I want you to notice is that we are looking for the change in the water. So we got some extra information here. We're told that the tank is 5 feet and the tank is 10 feet. This is not in terms of water. We only want in terms of the water, H2O. So when I write out my givens, I'm told that the change in volume is 2 cubic feet per minute. So I'm going to go dV dt, but be careful. We're going to make it negative this time, cubic feet per minute. You might be asking, why negative? Because it's running out. We are leaking water. We're losing water. And remember, if we're decreasing, our rate is negative. Remember up here, if we're decreasing, our rate is negative. We're also told that the height of the water is 4 feet. And we are out to find the change in height, dH dt. Okay, so now we got to come up with our equation. We need an equation to deal with volume, cones, and heights. Of course, we got the volume of a cone. 1/3 pi r squared h. Now, before we go any further, there's one bit of a problem right here. Okay, and that's this right here. We're in R and H. We only want one variable. 2 variables makes a big mess for us. So we have to convert R or H. So the question is, well, which one do we convert? Well, I look at what I'm given. I'm given height. So I don't need R. So I only want H's. So how do we do that? Well, now we can look at the tank. So we are now told that the tank has a radius of 5 feet. It's a conical tank, and it has a height of 10 feet. I can use this to determine a relationship between R and H by using similar triangles. You can use this skill a lot in here. So we can say r over h is the same as 5 over 10. Therefore, I can say r is 5 over 10. Whoops, 5 over. There we go. 5 over 10h, or r is 1/2 h. And I can plug that in. So now I would get v equals 1/3 pi r, which we're replacing with this 1/2 h. Don't forget the square h. Now I can take the derivative now, but I'd have to use product rule, and that's pretty nasty for this. But instead, what I'll do is I'll simplify this. If I distribute the 1/2 to the 2 to the square to the 1/2, we get 1/4. 1/4 times 1/3 is 1/12 pi. We get h squared times another h, so we get h cubed. And this is a much easier derivative to take. So speaking of which, let's go and take our derivative now. This is what we want. Everything's in terms of h. So now when I take the derivative, dv dt, don't forget we're with respect to time here, equals, drop down the 1/3, that means the 3, we get 1/4 pi h squared dh dt. Don't forget that chain rule. So there's my derivative. And I'm going to plug everything in. We're told dv dt is -2 equals 1/4 pi. The radius is, the height, is 4. We square that, we get 16 dh dt. Solving, therefore, dh dt equals -8 over 16 pi. Talk about units here real quick. So when we talk about the units, h is measured in feet. T is measured in minutes. So that's going to be -8 over 16 pi feet per minute. And now let's go ahead and write our answer. We would say the height of the water, and you can use H2O, when h is 4 feet, is negative, so is decreasing at a rate of 8 over 16 pi feet per minute. And there's our answer right there. Now, a couple of things I do want to point out to you is, one, when you're writing a fraction, let's say here, I got some space down here. When I'm writing this fraction here, I'm going to write it 8 over 16 pi. Don't write it as 8 over 16 pi like this, because the reader might see this as 8 over 16 times pi, and they're not the same. So we don't do that. We just leave your fractions horizontal. Don't do these cutesy slashed fractions right there. All right, we're actually going to take a look at number 6 at another time here. So we're not going to worry about that one just yet. So I hope you guys enjoyed the lesson. Go back and watch these if you need to again. Bye-bye.